In this session, we are going to perform a heat load calculation. There are many tools using which you can perform a heat load calculation. But here we are going to perform a manual heat load calculation step by step using an Excel tool to perform this calculation. We are going to use one E20 heat load calculation sheet. The name E20 arises from a heat load calculation done through 20 steps. Hence the name E20 form. I have also attached a carrier handbook with this lecture which will be guiding us through this calculation. For any future calculations using this E20 form, you can refer that guidebook. So first let's take a look at the problem for heat load calculation. We are going to perform a heat load calculation for air conditioning of room. So here the problem that is stated here is we have to calculate the heat load of an office room. The dimensions of which are provided below. The location is the city of Atlanta in the state of Georgia, United States. The room details are as following. The dimension of the room is 25 feet by 20 feet by 14 feet height. The thickness of the wall is 8 inches. The material of the wall is solid brick. The thickness of the roof is 12 inch. The material of the roof is concrete. The thickness of floor is 8 inch. The material of floor is concrete. There are 2 glass windows in here and the dimension of each is 6 feet by 4 feet and 1 inch thick. The total quantity of glass windows are 2. The type of glasses, double pane, ordinary non-painted. The dimension of door is 4 feet wide and 7 feet height. The room temperature that has to be maintained is 72 F and the humidity of the room that has to be maintained is 50%. The total occupants of the room is 20 and the total number of workstation is 20 each consuming 400 watts of power. Total number of printers are 2 each consuming 340 watts of power. There are 10 lighting installations in the room. Each lighting installation consumes 30 watts of power. The ventilation is as per standards. The room that has to be air conditioned is at the ground floor. There is no floor above this room and the roof is shaded. The north and east side of the room is exposed to the mentor. And the west and the south side are partitions, which means there is another room on the other side. I have simplified this E20 calculation sheet or the calculation form. Simplifying it helps us to mark the calculation more efficiently. So in a 20 form, let's first fill up the name of the project, which is heat load calculation. Next, the location. The location is Atlanta, Georgia. Before starting the calculation, we need to fill up a few details in these fields. Here first is the detail of the floor. This is a room at ground floor. The space references of his room. The total area by the square feet is 25 multiplied by 20 feet equals to 500 square feet. The height to the ceiling is 14 feet and thus the volume of the room is 7,000 cubic feet. The target air temperature and the humidity is provided, which is 72 F and 50% relative humidity. From here, we have to calculate the wet bulk temperature and the humidity ratio, which is the grains of moisture per pound of air. The value of grains per pound will help us in calculating the latent heat of the room. As a designer, we always design for the worst case scenario. We do not design for an intermediate condition. Although the worst case scenario is far less prevalent over the year. The reason is because if we design for intermediate conditions and when the worst case scenario arises, even though it is very less, maybe for 4 or 5 days or even 1 week in a year, then in those conditions, the system that you have designed for might fail, which is going to result into customer dissatisfaction. Thus, as a result, we always design for a worst case scenario. Most of the time the customer specifies the driver temperature with which we are gonna work. But if that is not specified, there is a way to find it out. The website ashmeteor.info provides us the climate conditions or the weather conditions of multiple weather stations situated all around the world. Here we are searching for the weather conditions at Atlanta, Georgia. One can directly search with the name of the place in here, the search field, and since we know where the location of the city is, we are gonna zoom in here to find out all the weather stations around the city. Just right, click on the screen where the city is located. The balloons here attributed with ABCD are the weather stations around where we clicked. We are going to consider the weather station at Atlanta Hartsville Jackson Airport before clicking on this balloon. Make sure the data is the latest one. So click on the 2017 database and make sure the units are in inch/pound. So let's click on the balloon that denotes the registration at Hartsville Jackson Airport. Once we click on it, all the weather data around the year appears on the screen. The tab that we are going to consider here is annual cooling, humidification and enthalpy design conditions. There are other tabs that states the heating and humidification conditions also. And there are other tabs that states the minimum and maximum conditions of weather. Here, we are going to refer to annual cooling day humidification and enthalpy design conditions. Kindly refer to the sub-tab cooling drive in NCWP. Here, MCWB means mean coincidence wear temperature. Here, you will notice that the DR temperature and the NCWB are for 0.4%, 1% and 2% conditions. As a designer, we will always consider the 0.4% conditions, which means 0.4% condition is the worst case scenario that is gonna happen all around the year, which means the worst case scenario, which is the driver temperature of 94 F, is gonna occur 0.4% of the times all around the year, which means 365 days, multiplied by 0.4%, which is the worst case scenario, is going to occur all around the year for 14.6 days. Thus, we have to design for these conditions so that our design doesn't fail. Even for the worst case scenario of 0.4%, here for 0.4%, the driver temperature is 94 F. This is specific to the location. So let's fill in the arrival temperature of the ambient condition. It is 94 F. Next is the wet bulb temperature. We have to find out from here in the 0.4% tab. Just next to the arrival temperature is the MCWB, which is the mean coincident wet bulb temperature. The mean coincidence is nothing else but the arithmetic mean of all the wet bulb temperature, this 0.4% period. Let's take in the value 74.2 F, which is the MCWB, and add it in here. Now we have to find out the relative humidity and the grains per pound for the triable temperature of 94 F and a viable temperature of 74.2 F. At the same as me.info website. We'll find a psychrometric calculator in future. We are going to find out this value referring to a psychrometric chart. But as of now, we are going to refer to this psychrometric calculator. So let's input all the values that we have found out here. The driver temperature is 94 F and the volt temperature is 74.2 F. After doing that, click on this check mark, and consequently, the rest of the values will be displayed. On the left, this is the relative humidity. On the right, this is the dew point temperature for the above dry bulb and the with bulb temperature. So the relative humidity is 39.7. Let's fill in that value in here and here. The humidity ratio or the grains per pound is 95.41. So let's add the value here. Now we have to also find the relative humidity and the grains per pound for the target room drive temperature and we bulb temperature. So let's reset the value and input the values for the target room temperature. So the target drive temperature is 72 F. Let's put it in there. And the next, the target relative humidity of the room is 50%. Once we input this, we are going to click this check mark, which means we are going to find this above value with the above triable temperature and this relative humidity value. Thus, the val temperature of the room is 60.1 F. The dew point is 52.4. So let's add the temperature of the room and the dew point temperature of the room, and the value of grains of moisture per pound of air is 58.48. Let's take this value and add it in here. Now, we got the difference of all the values that is required to perform our future calculation. The difference in Dr. temperature of the ambient and the target room condition is 22 F and grains per pound is 36.91. The difference of value of tribal temperature and grains per pound will be used in future. So let's now start with the calculation for solar gain through glass. As in the screen, we can observe that the glass windows are situated in the north and east side of the room, and the dimension of the glass is 4 feet by 6 feet and 1 inch in thickness. Thus, the area of the glass is 4 multiplied by 6 equals to 24 square feet. Next, we are going to refer to the carrier handbook in which we are going to find out the amount of heat gain per square feet of this double pin glass. The thermal radiation jury depends upon the latitude of the location here at Atlanta, Georgia. It is 33.6 feet northwards to find out the solar gain at 30 degrees latitude. We have to refer to table 15 at page 47 of the carrier handbook. Since the glass window are situated on the north and the eastern side, we are going to find out from this table the highest value in north and the east. The reason we consider the highest value is because we designed for the worst case scenarios here. The highest value for the north and the east is 33 and 165 respectively. Next, we have to find out the factor for solar heat gain for the type of glass. Keep in mind, this is a double pane glass. To find out the factor, we have to refer to table 16 at page 52 of the handbook. Here, you can see for the double pane ordinary glass, the factor is 0.9. So we are going to add the factor 0.9 in this film, and hence, we are going to find out the heat gain through this glass windows, which is 712.8 and 3564. Next, we are going to find out the transmission gain through walls and roof. First, let's refer to the problem and the layout diagram and find out and fill in the total surface area of each wall and the roof. From the layout, we know the surface area of the north wall is 350 square feet and thus the south wall is the same as 350 square feet. The surface area of the east wall is 280 square feet and the west wall is the same as 280 square feet. Next, the roof is 500 square feet as we can see on the table on the right, which we have plotted earlier. The difference in driver temperature is 22 F. So we are going to fill out the difference of the TD of 22 F for the north and the east wall, which are the exposed. But for the partition wall, we are not going to consider the exact difference of 22 F. The reason being the room on the other side might not be that high of an AM temperature. So as part of our intuition, we are going to reduce that, let's say to an ambient temperature of 86 F. Now, the difference stands at 14 F. So for the wall with the partition, the TD that we are going to consider is 14 F. But for the roof, the TD is the same as the north on the east wall, that is 22 F. Next, we have to find out the U factor or the thermal conductance of each of the wall. Keep in mind the walls are made up of brick and the roof and the floor are made up of concrete, 12-inch and 8-inch respectively. The thickness of the wall is 8-inch and the thickness of the roof is 12-inch. To find out the U factor of the wall on the roof, we have to refer to table 21 at page 66 of the handbook. Since the brick wall is 8-inch in thickness, we are going to consider the U factor of a sandplastered wall. The U factor for that type of wall is 0.45 bushels per hour per square feet per degree Fahrenheit. And for a 12-inch concrete with sand cluster with a concrete density of 140 pounds per cubic feet is 0.52. Once we add this in the field, we find out the heat gain through the wall and the roof. The unit of rate of heat gain is bit2 per hour, which can also be referred to as kilowatt. This is the same unit that of power in inbound system. The unit is bit2 per hour, and in SS system, it is kilowatt 1. kilowatt equals to 3,412 bushels per hour. Next, we are going to find out the transmission gain of heat through the glass windows and the floor. Previously, we found out the thermal radiation through the glass. Now we have to find out the heat gain through the glass by the means of conduction and convection. So from the problem stated in prior, the area of each glass window is 24 square feet and thus multiplied by 2 is 48 square feet. Here, we are accounting for both of the glass windows. The difference in temperature between the ambient and the inside room is 22 F. Hence the TV is 22 and to find out the value of thermal conductance for glass, we have to refer table 33 at page 75. Here, the transmission coefficient for a double-pin glass within a half-inch airspace is 0.55. So once we fill out the value of 0.55, we find out the heat gain through transmission through the glass window. Next, we have to find out the heat gain through the floor. Here, the area of the floor is 500 square feet. Since the temperature beneath the floor is far less compared to the ambient air outside, we are going to reduce the TV, just as in the previous exercise, to 14F and referring to table 21 and page 66, we find out the transmission coefficient of the floor. Since the floor is of concrete and 8-inch thickness, we find out the thermal coefficient of the floor to be 0.49 per gypsum board, with a gypsum board plaster. So once we fill out the thermal coefficient here, we find out the value of heat gain through the floor. Next, we have to find out the sensible heat gain through air infiltration. In one of the previous sessions, we have discussed about how air infiltrates through those windows and cracks on the boundaries of the room. Here, we are going to just consider the air infiltration through the door and not through the windows or any cracks. There is no definite way to calculate the air infiltration inside a room through a door because there are times the door will be opened in a room is highly arbitrary in nature. One cannot possibly know, and there are tell values, and those tell values differ with each other with a large margin. So here we are going to figure out the area infiltration through a small calculation by ourselves. As from the problem stated in prior, there are 20 persons occupying a room. Let's say in that office space, each person needs to make a transit in the room 7 times a day. So for each transit for entering and exiting the room, one person will open the door 2 times. So that means the person will open the door 14 times a day, which means 20 person will open the door 280 times a day. Now, the weight of the door is 4 feet, opens from a sharp position at an angle of 90 degrees. Just to calculate the volume of air displaced by the door, we have to find out the area of the door through which the dome makes a sweep, that is pi r squared divided by 4. And now when we multiply this area by height, which is 7 feet, we find out the volume of the air that this door displaces. Next, we have to find out the volume of the door that has been displaced 280 times a day. Hence, we have to multiply this value by 280 times. Now we have to calculate the volumetric flow of air infiltration into the room. Hence, we have to bring in a factor that is time. We have to divide this value by 24 multiplied by 60, find out the volumetric flow per minute. Hence, we find out the value of air infiltration. Volumetric flow is 17.1 cfm. Now we are going to plot the 17.1 cfm in here. And since the number of door is 1, we are going to fill in the value 1 in here. Next, the temperature difference of the ambient with the inside of the room is 22F and thus multiplied by a factor 1.08. Hence, we find out the value of heat gained in the room by air infiltration. Next, we are going to calculate the value of the sensible heat generated by the occupants of the room. As stated in the problem previously, there are 20 occupants in the room, and to find out the heat generated per person, we have to refer to table 48 at page 99 of the Carrier Handbook. Since the temperature of the room that has to be maintained is 72 F, we are going to consider the value of room temperature as 70 F in here. Since this is an office, we are going to consider the value of heat generated by an office worker. The sensible heat generated by an office worker here is 285 bushels per hour, and the latent heat generated by an office worker is 165 bushels per hour. We are going to fill in this value in here, and thus, we find out the sensible heat generated by the total occupants of the room. Next is the lighting load. In the previous statement, it has been mentioned that there are a total of 10 light installations in the room. Hence the total power consumed by all the installation is then multiplied by 3300 watt, multiplied by 3.412. We convert this hour and hence, we find out the value of heat generated due to lighting. Sometimes from the customer's specification, we can find out the total power consumed due to lighting. And sometimes the customer does not specify that. In those cases, we take a thermal value of 1 watt of square feet of lighting. Next is the heat load duty equipment. This we can find out from the customer's specification. As per the customer's specification, there are 20 watt stations of 400 watts power each. Thus all the workstation will consume 400 multiplied by 20, that is 8000 watts of power. There are total 2 printers in the room consuming 340 watts of power. So the total power consumed by 2 printers is 680 watts. So the total power consumed due to the equipment in the room is 8680 watts. Since we have added all the equipments under one value, we are going to depict the number of equipments as 1. Hence converting it into bit 2 power, we get the heat load from all the working instruments inside the room. Next is the latent heat generated by air infiltration and the people, that is occupants inside the room. As we know, the air infiltration value is 17.1 cfm. The difference in grain compound is 36.91, which we have found earlier, and multiplying it by a factor of 0.68 we find out the latent heat contained due to the air infiltration. Next is the latent heat generation due to occupants. As per customer specification, there will be 20 occupants in the room, and previously referring to table 48 of page 99, we have found out the latent heat per person is 165 Bg per hour. Hence, multiplying these values, we find out the latent heat content generated by the occupants. Next, we have to find out the sensible heat content due to the ventilation. To find out the value of ventilation, we have to refer to table 45 at page 96. Ventilation can be calculated in 2 different ways. One is CFM per person and another one is CFM per square feet of floor, as we have discussed earlier. As designers, we always have to prepare for the worst case scenario. Hence, we have to consider the highest value of CFM per person or CFM per square feet of floor. We do not consider both the values simultaneously, but one or the other from the table in the screen. We can find out the ventilation airflow required in an office is 25 cfm per person. And similarly, for the same office, the ventilation of air required per unit area of floor is 0.25 cfm per square feet. When we plot the value of cfm per person required in an office, which is 25, and multiply it by the occupant, that is 20, we find out the total ventilation required is 500 cfm. And next, we find out for an office, the value of air ventilation in cfm required per square feet is 0.25, and the total floor area of that office is 500 square feet. Hence, we find out the value, which is 125 cfm. Thus, we are going to consider the value which is the highest, that is 500 cfm. Thus, to calculate the sensible heat and the latent heat of the room, we have calculated the airflow for ventilation required is 500 cfm. Now, as we know the temperature difference between the inside of the room and the outside, ambient is 22°F. Next comes in a parameter which we call a contact factor. Contact factor is 1 minus bypass factor. We have discussed about Beer's factor in one of our sessions, where we have discussed the ventilation heat load in a room. To find out the bypass factor, we have to refer to table 62 of page 125 of the Carrier Handbook here. As you can see, for typical comfort application, the bypass factor here is in between 0.120 0.2. We are going to take an intermediate value which is 0.15. Hence, adding the value in this field of 0.15, we find out the contact factor to be 0.85. Once we find out the contact factor here, The ventilation airflow multiplied by the temperature difference between the outside air and the inside air multiplied by the contact factor multiplied by a factor 1.0. Hence, we find out the value of heat gain due to air ventilation inside the room. Similarly, to find out the latent heat content due to ventilation, we have found out the ventilation airflow and the difference of grain per pound, which we have found out previously. We know the contact factor, and multiplying it by a factor of 0.68, we find out the total value of latent heat content due to air ventilation. Now, adding all the above calculated values, we find out the subtotal heat load content. But for every design, we have to add a safety factor to the subtotal value. This safety factor helps us to consider whatever the answer weighs the room can gain heat. Here, the safety factor that we have taken is 10%. That means the 10% of the subtotal value, which is this one. Next, when we add the subtotal value and the safety factor, we get the final total heat load, which is this value. And we convert that to tonnage of refrigeration. 1 tonnage of refrigeration equals to 12,000 bushels per hour. Thus, through all the above processes, we find out the total heat load of the room is 7.83 tonnage of refrigeration. That means to remove all the heat from the room and bring down the temperature of the room at 72 F and 50% relative humidity, we have to design for refrigeration equipment having a capacity of 7.83 TR.